Section 1.4 talks about, among other things, changes. And by changes, in chemistry, we're talking about changes typically of one substance to another, or in the case of physical changes, in the change of a form of a substance to another form, typically between different states of matter, such as solids, liquids, and gases. So if we look at this example here of a pot of water boiling, the water in this particular example is undergoing a physical change. A change from the water state, where the molecules are in contact but free to move relative to each other as long as they stay in contact, to a gas state, where the molecules are completely free from interactions with each other and are actually just moving randomly about whatever container is containing them. Physical changes are ones that take place that are typically reversible, either through rearrangement, reattachment, if it's just a physical change like dividing or cutting up a substance, or in the case of changes of state, such as the second example as well, where we have dry ice turning from a solid to a gas, you can actually change things back again from the change that you've just performed on them just by altering the temperature. So dry ice, if it's warm enough, will sublimate, meaning go directly from a solid to a gas. If we actually cool down CO2 gas again to a cold enough temperature, we will actually see the reverse process occur, where we get a change in state, a physical change, back from gas back to a solid. Now, a chemical change, on the other hand, involves a change of chemical attachments. So the atoms that make up a particular substance in the compound or item that we start with is going to have to rearrange and cause new attachments to form or new attachments to break to end up with a different set of attachments for the final product. So in this case, we're looking at an example of iron atoms within a nail, and that same set of iron atoms, after they have combusted or rusted, as we more typically call it, into iron oxide, which is rust. So in this case, the oxygen molecules that are floating around as part of our air have combined and become part of the chemical structure of this particular object. So making iron oxide, where we have these iron atoms and oxygen atoms interbonded between each other in a crystalline structure here, and that represents a change in the attachment of the atoms to each other. Now that's different than the attachment of one molecule to another of the same exact substance. Before, when we were talking about dry ice or water, even though the interactions between one water and another water might change as they go from a solid, a liquid, or a gas, or back again, the molecules involved were still water. In a chemical change, what we're seeing is that the substances turn into something new. So that's a key aspect of this. A new compound or substance is formed. So that's the main difference here between a physical and a chemical change. So one way you can tell just by observation whether or not you have a physical or a chemical change is to look at what the effect of temperature would be on that particular substance. So for ice, for instance, you know that it's a physical change when it goes from a solid to a liquid, because by changing the temperature back to colder again, you can recover the solid form of water, which is ice. The other possibility is if you are just causing a physical alteration of that particular substance's secondary or main macroscopic structure, by say cutting it into pieces, or in this little example, removing someone's hair. If you could theoretically physically reattach it, then what you have done is actually just a physical change. The hair is still hair, it's just no longer in the place in the attachment to the head that it was originally. So now with a molecular change, let's look at one difference here. On the left, we have a physical change. We want to compare and contrast this. So water molecules is liquid going to gas with heat. We see that this is likely a physical change because when we remove the source of heat and make this system colder, we end up with liquid water again. While in the second example, which is a chemical change, we're actually seeing that hydrogen peroxide, which is a hydrogen attached to an oxygen, attached to another oxygen, a hydrogen, and a line here, kind of a squiggly line, but they're all attached one after the other in sequence, can actually decompose, which means kind of break apart into simpler substances, and we'll end up with oxygen molecules and a couple of water molecules. So what we end up with at the end is not just a different state of matter, solid, liquid, or gas of hydrogen peroxide, but what we actually end up with is a new, or in this case, a couple of new substances. So that's how we know that a chemical change has occurred. So let's take a look at this example. I want you to try and determine if this particular change of sugar going from a solid to a dissolved, or what we refer to as an aqueous substance, is a chemical or a physical change. Now remember, you want to look at this in terms of whether or not we have a change in the actual chemical substance from one substance to a new one, or whether or not there's just been a physical rearrangement or state change present. Okay, so go ahead and pause the video, think about it. Alright, I'm assuming you've unpaused the video at this point, and you are back. This is a physical change. And we know it's a physical change because even though the sugar molecules, which are solid, are now dispersed amongst a set of water molecules, there is no breaking of attachments of bonds between any of the atoms in the sugar molecule or rearrangement to new bonds. There are no breaking or rearrangement of bonds in the water molecules either. So the water and the sugar are mixed, but they are not different substances. They're the same substances we started with. So that's how we know this is a physical change. All right, how about propane gas burning? Same thing. Tell me whether it's a physical or a chemical change. Okay, so I'm assuming that you've paused it and unpaused it at this point. We look at what we start with. It's propane, which is C3H8, meaning 3 carbons, 8 hydrogens. And these molecules are reacting with oxygen. And the oxygen that they're reacting with is resulting in 2 new compounds, carbon dioxide and water vapor. So what we start with is a different chemical species than what we end with. So this obviously must be then a chemical change. So here's a whole bunch of them. Let's try them all. Start with the eggs. So pause it as you need to try and think about it, come up with your idea. Okay, so with the eggs, we have to go a little bit more by experiential or observational estimates of whether this is a chemical or a physical change, because we don't have the molecular structure of egg written here anywhere, do we? In fact, eggs are a pretty complex mixture. But we can kind of apply the idea of, if we change the temperature, will it go back to what it started as? Or is there any way to subdivide it or chop it back up into pieces or separate the pieces to get it back to what it started as? And no, there really isn't. There's no way to uncook an egg just by changing temperature or anything like that. It's kind of like a cake. You can't just kind of cool the cake back down and get flour and eggs and butter and sugar back again. Once you put all that together and it's mixed, there's been some chemical changes that have occurred. And that makes it a chemical change. Okay? So how about boiling some water? Yep. That's a physical change. Changing the temperature will result in a change back to the original state, original observations of what that compound looks like. How about this change? We're changing acetone to acetone that's a little bit more spaced out. Obviously a physical change, right? Nothing has changed about the bonds and attachments of the molecules. Okay, here we have methane and oxygen. After the change is done, we have water vapor and carbon dioxide. Yep, chemical change. Okay, and here we have liquid water going to gas water, so that's another pretty much the same exact situation we have here, but we're showing it on a molecular scale. So that means it's physical.